Hey everyone, welcome to another tutorial on using C# and AI. Before we dive into writing C# code and exploring AI, let's take a moment to understand what AI really is. Getting a grasp on the fundamentals is crucial for building a broader understanding. Artificial intelligence has come a long way since it first started. In the beginning, AI was all about traditional algorithms, sets of rules designed to solve specific problems. These algorithms, like sorting and searching techniques, followed fixed steps to get the job done. But then, AI research took a big leap forward with machine learning. Unlike traditional algorithms, machine learning algorithms allow systems to learn from data and get better over time. This was a game changer, making AI more adaptive and intelligent. Take bubble sort, for example. It's a traditional algorithm that sorts a list of numbers by following a specific set of instructions. On the other hand, a machine learning algorithm like linear regression learns from data to make predictions, like forecasting exam scores based on hours studied. This shift from static algorithms to dynamic learning models has really boosted AI's abilities, letting it tackle complex tasks like understanding human language and recognizing images. One of the most exciting advancements in AI is neural networks. These are inspired by the human brain and are capable of learning from vast amounts of data. Neural networks power some of the most advanced AI applications, from self-driving cars to voice assistants. In this video, we'll explore AI's journey, highlight key milestones, and show you the differences between traditional algorithms and machine learning algorithms. And to make things even more interesting, we'll create a custom neural network from scratch using C# so you can understand how it all works. The previous segment, including the audio you're currently listening to, was created using artificial intelligence. This demonstrates how seamlessly AI has become a part of our daily lives, often without our immediate awareness.
Now that we have an overview, let's explore some fundamental concepts and algorithms that form the backbone of this technology. We'll start with traditional algorithms like bubble sort, which lay the groundwork for more complex systems. Then we'll delve into machine learning, which empowers systems to learn from data and make predictions. Finally, we'll touch on neural networks, which mimic the human brain's ability to process information. These concepts will help us appreciate how AI works behind the scenes and the potential it holds for the future. Bubble sort is a simple sorting algorithm that works by repeatedly stepping through the list, comparing adjacent elements, and swapping them if they are in the wrong order. This process is repeated until the entire list is sorted. In a descending bubble sort, the largest values bubble to the top with each iteration. The algorithm stops when a complete pass through the list results in no swaps, indicating that the list is fully ordered from highest to lowest. This algorithm solves the sorting problem by taking a list as input, sorting its values, and then providing the sorted list as output. Essentially, bubble sort is a mathematical function that processes the provided input to produce the desired output. Now that we have a grasp on traditional algorithms, let's move on to something more advanced, machine learning. Unlike traditional algorithms that follow a fixed set of rules, machine learning algorithms enable systems to learn from data and improve their performance over time. One of the simplest and most commonly used machine learning algorithms is linear regression. Linear regression is a basic but powerful machine learning algorithm used to model the relationship between a dependent variable and one or more independent variables. It works by fitting a linear equation to the observed data. Here's a breakdown of the code. Main method, we start with sample data, hours studied, and the corresponding exam scores. We calculate the coefficients, intercept, and slope of the linear regression model using the calculate linear regression method. We then use these coefficients to predict the exam score for a given number of hours studied using the predict exam score method. Finally, we print the predicted exam score. Calculate linear regression method. This method calculates the slope and intercept of the linear regression model using the least squares method. It computes the sum of the x values, hours studied, the sum of the y values, exam scores, the sum of the products of x and y, and the sum of the squares of the x values. Using these sums, it calculates the slope and intercept of the best fit line. Predict exam score method. This method takes an input value, hours studied, and uses the linear equation predicted exam score equals intercept plus slope multiplied by hours studied to predict the exam score. With this simple linear regression model, we can now make predictions based on our data. This is a basic example of how machine learning can be used to find patterns and make predictions. In contrast to bubble sort, linear regression marks a step forward in AI's evolution. Instead of following rigid rules, it learns from data to predict outcomes. This shift from static algorithms to data-driven models exemplifies the progression towards more intelligent systems. While bubble sort efficiently sorts a list by repeatedly organizing elements, linear regression looks for patterns in data to make informed predictions. It doesn't just process inputs according to a fixed procedure, it adaptates to the nuances of the data provided. This transition from simple rule-based processing to adaptive learning systems underscores the broader journey of AI, moving from clearly defined manual instructions to more sophisticated autonomous decision-making. As we delve into machine learning and neural networks, we'll explore even more advanced capabilities that push the boundaries of what AI can achieve. Neural networks are a significant advancement in AI, inspired by the human brain's structure. Unlike traditional algorithms like bubble sort, which follow fixed rules, neural networks consist of interconnected layers of nodes that can learn and adapt. This learning process, called training, involves adjusting internal parameters based on data, making neural networks excellent at recognizing patterns and handling complex tasks. They are especially useful for analyzing unstructured data, such as images and speech, and are the foundation of many cutting-edge AI applications. As we explore neural networks, we'll see how they open new possibilities for technology and innovation. Now, let's explain the picture that represents a neural network. As stated previously, neural networks draw parallels to the human brain, which they're designed to mimic. Imagine the input layer as your senses, the ways you perceive the world. Just like your eyes and ears collect information, the input neurons labeled X1 and X2 receive data from the outside world. These inputs could be anything, like the dimensions of a picture or the features of a sound. The information then moves to the hidden layer, similar to the brain's cortex, where complex processing happens. This layer, with its 4 neurons, H1, H2, H3, and H4, acts like a network of neurons in your brain that interprets and makes sense of the sensory data. Each hidden neuron processes the information by adjusting weights and biases, akin to how your brain strengthens or weakens connections between neurons based on new experiences. These adjustments enable the network to understand patterns and nuances in the data, much like how the brain learns from experience. Finally, we arrive at the output layer, represented by the neuron Y. This is comparable to making a decision or forming a response. In the brain, after processing sensory information, you might recognize an object or respond to a question. Similarly, the output layer of a neural network provides a result, like identifying an image or predicting a value. The connections between the neurons, represented by lines in the diagram, function like the synapses in the brain. These connections carry signals between neurons, and the weights represent the strength of these signals. Just as your brain strengthens connections between neurons based on learning, a neural network adjusts these weights during training to improve accuracy. Although our diagram doesn't show it, each neuron in the hidden layer uses an activation function, much like how neurons in the brain fire or don't fire based on certain conditions. This nonlinear processing helps the network handle complex and varied data. In essence, a neural network is a simplified model of the human brain. It learns from data by adjusting the connections between its neurons, just as the brain learns from experiences by forming and modifying synaptic connections. To sum up, neural networks are inspired by the way our brains work, using layers of interconnected neurons to process and interpret information. This analogy helps us understand how these systems can learn to perform tasks, from recognizing speech to predicting outcomes. Now let's create the custom neural network step by step. We begin by defining the neural network class. Inside this class, we declare 3 private fields: weights list to store the weights between layers, layers to store the number of neurons in each layer, and learning rate to control the speed of learning during training. In the constructor of the neural network class, we initialize these fields. The constructor takes 2 parameters, an array of integers, layer sizes representing the number of neurons in each layer, and a double LR representing the learning rate. We assign layer sizes to the layers field and LR to learning rate. Next, we initialize the weights list, which will hold the weight matrices between each layer. The number of weight matrices corresponds to the number of connections between layers. So we iterate through the layer sizes array, starting from the second element. For each pair of consecutive layers, we initialize a weight matrix with the initialize weights method. This method is called with two parameters, the number of neurons in the current layer and the number of neurons in the previous layer. The initialize weight matrix is then added to the weights list. This process of initializing weights is crucial as it determines the starting point of the neural network's training. Proper initialization can help in faster convergence during training by ensuring that the neurons in the network are activated efficiently. The initialize weights method, although not shown here, and we will create it in the next step, would typically involve creating a matrix filled with small random values. These values are the initial weights that will be adjusted during the training process to minimize the error between the predicted output and the actual output. The initialize weights method begins by creating an instance of the random class named R&D. This object will be used to generate random numbers, which are crucial for initializing the weights of our neural network. The method then declares a 2D array called weights, with dimensions defined by the parameters rows and columns. These dimensions correspond to the number of neurons in the current layer and the previous layer, respectively. Next, the method uses two nested loops to iterate over each element of the weights array. The outer loop runs through each row, representing the neurons in the current layer, while the inner loop traverses each column, representing the neurons in the previous layer. Inside these loops, we assign each element of the weights array a random value generated by the random next double method minus 0.5. The next double function generates a random number between 0.0 and 1, and by subtracting 0.5, we center these values around 0. This means the weights will initially range from negative 0.5 to 0.5, providing a balance of positive and negative values. Finally, the method returns the weights array, now populated with these random initial values. These initial weights are crucial as they determine how the input signals will be processed and transformed as they pass through the network. Proper initialization can help the network converge more efficiently during training by ensuring diverse activations across the neurons. This setup lays the groundwork for the neural network's learning process, where these weights will be updated and refined to minimize the error between the network's predictions and the actual targets. The train method begins by setting up a forward pass through the network. We start by initializing a list called layer outputs with the input data inputs. This list will store the outputs of each layer as the data progresses through the network. We also set current outputs to the inputs to keep track of the current layer's output. We then proceed with the forward pass, iterating through each weight matrix in the weights list. For each weight matrix, we calculate the output of the next layer by calling the activate method. This method applies the weights to the current outputs to produce the next layer's outputs, which are then stored in layer outputs. This process continues until we reach the final output layer, producing the network's predictions. Next, we move to the backward pass, which is crucial for learning. We initialize a list called deltas to store the error gradients for each layer. Starting from the output layer, we calculate the difference between the target values and the predicted outputs stored in targets and current outputs, respectively. This difference, or error, is used to compute the output layer's delta values. We multiply the error by the derivative of the activation function, sigmoid derivative, applied to the current outputs. These deltas represent how much we need to adjust the weights to reduce the error. The backward pass continues through the hidden layers. For each hidden layer, we calculate the deltas by propagating the error backward from the subsequent layer. We sum the product of the next layer's deltas and the corresponding weights. This sum gives us the total error contribution from the next layer's neurons. We then multiply this error by the derivative of the activation function for the current layer's outputs to obtain the hidden layer's deltas. We insert these delta values at the beginning of the deltas list to maintain the correct order. Finally, we update the weights using the calculated deltas For each weight matrix, we iterate through each element and adjust it by adding a term proportional to the product of the learning rate, the corresponding delta, and the output of the previous layer's neuron. This adjustment moves the weights in the direction that minimizes the error, effectively teaching the network to make better predictions. This process of forward and backward passes, followed by weight updates, is repeated for each training example, allowing the neural network to learn from the data. The train method encapsulates this core learning algorithm, enabling the neural network to iteratively improve its performance on the given task. The activate method is responsible for calculating the outputs of a layer in the neural network based on the inputs and the weights associated with that layer. The method starts by creating an array called outputs, which will store the results for each neuron in the current layer. The number of elements in this array corresponds to the number of neurons in the layer. To determine the output for each neuron, the method calculates a weighted sum of the input values. It does this by multiplying each input by a corresponding weight and adding these products together. This sum represents the total input to the neuron before applying an activation function. After computing the weighted sum for each neuron, the method applies the sigmoid function to this sum. The sigmoid function is an activation function that helps in transforming the weighted sum into a more manageable range. It essentially squashes the output values to lie between 0 and 1, making them easier to interpret, especially when working with probabilities. The result of this transformation is then stored in the outputs array. Once all neurons have been processed, the activate method returns the array of outputs, which serves as the input to the next layer in the network. Moving on to the sigmoid method, this function is used to transform the raw input into a range between 0 and 1. This transformation is crucial as it helps in normalizing the outputs, ensuring they are within a consistent range regardless of the input size. The sigmoid function smoothly transitions from one value to another, which is useful in neural networks as it allows for a gradual and differentiable change in output. Lastly, the sigmoid derivative method provides the rate at which the sigmoid function's output changes concerning its input. This is important for the backpropagation process during training, as it tells us how much to adjust the weights to reduce the error. The derivative indicates the sensitivity of the output to small changes in the input, which helps in fine-tuning the network's weights. This sensitivity information is used to update the weights more effectively, guiding the learning process by adjusting them in the right direction to minimize errors. Together, these methods, activate, sigmoid, and sigmoid derivative, are essential for the neural network's ability to process inputs, produce outputs, and learn from the differences between its predictions and the actual targets. They help the network transform data, interpret it, and adjust its internal parameters to improve accuracy over time. The feed-forward method is designed to pass input data through the entire neural network to generate an output. This process is fundamental to making predictions with the network. The method begins with an array of inputs representing the initial data fed into the network. It then iterates through each set of weights stored in weights list. These weights correspond to the connections between the layers of neurons in the network. For each layer, the method calls the activate function, passing the current set of inputs and the weights associated with that layer. The activate function processes these inputs by applying the weights and an activation function, transforming them into the outputs of the current layer. These outputs then become the inputs for the next layer in the network. This process repeats for every layer, effectively feeding forward the data through the network. As the data moves from the input layer to the output layer, it is continually transformed, capturing increasingly complex patterns and relationships within the data. Finally, the method returns the transformed inputs, which now represent the final output of the network. This output could be a prediction, classification, or any other type of result the network is designed to produce. In summary, the feed-forward method encapsulates the entire process of moving data through the network, applying transformations at each layer to arrive at a final output. It's an essential function that enables the neural network to make predictions based on the learned weights and the structure of the network. Now we're going to test our neural network with some actual data and see how it learns to make predictions. First, we define the structure of our network. We have two input neurons because we're feeding in two pieces of information: hours studied and exam score. We set up 9 neurons in the hidden layer and think of these as the brain cells of the network and helping it learn patterns. Finally, there's one output neuron that will tell us whether the student passes or fails. This structure is captured in the array layers 2, 9, 1. Next, we create our neural network with this structure and a learning rate of 0.1. The learning rate is like the speed at which the network learns. Too fast, and it might miss important details. Too slow, and it takes forever to learn. We're aiming for a balance. Now let's look at the training data. We have a list of input-output pairs. For example, 0.7 means 2 hours of studying and a 70% score. The output 0 or 1 tells us if the student fails or passes. We have a few examples, like studying 8 hours and scoring 85%, which is likely a pass. We set our training to run for 10,000 epochs. An epoch is just a fancy word for one complete run through all our training data. More epochs mean more opportunities for the network to learn and improve. In our training loop, we go through each epoch, and within each epoch, we train on all our examples. The train method helps the network adjust its internal settings or weights based on the differences between what it predicted and what the actual answers were. Every 1,000 epochs, we pause and check how well the network is doing. We calculate something called the mean squared error, MSE, and accuracy. MSE tells us how far off our predictions are from the actual values on average. Lower MSE means our predictions are getting closer to reality. Accuracy, on the other hand, is simply the percentage of correct predictions. To evaluate the network, we use the evaluate function. It runs the inputs through the network to get predictions, then checks how close these predictions are to the expected outputs. It also checks if the network's predictions are correct, rounding them to the nearest integer for simplicity. Finally, we have a fun little function, interpret MSE, that gives a qualitative interpretation of the MSE score. It tells us whether the performance is excellent, good, or needs improvement. So in a nutshell, this setup allows our neural network to learn from data, improve its predictions over time, and give us a good indication of how well it's doing. It's like teaching a child. Practice, feedback, and a lot of repetition help the network get better and better at its task. Thank you so much for tuning into this tutorial on building a neural network with C# and AI. If you found this content helpful, please give it a thumbs up and consider subscribing to our channel for more. In our next video, we'll dive into the exciting world of large language models and show you how to create a simple chat system. You won't want to miss it, so stay tuned and hit that notification bell to get updates on our latest content.